So far, I've painted a rather utopian picture of how automated this machine learning can be, that you just wrap, classify or predict around your data and magic happens and predictions are made. Of course, in the real world, there are messy, complicated problems to deal with, and I wanted to talk about two of the most important ones that are also fairly straightforward to deal with in dealing with the data that isn't quite right. So really those are to do with unbalanced data or unbalanced outcomes. Let's look at unbalanced data first of all. I'm going to illustrate it first of all with an example which will give a fairly poor prediction. So this is perhaps trying to predict somebody's height, somebody's sex from their height. So we've got a data point here of a 1.82 m person who is male, and we've got some more examples, and a 1.60 m person who's female. And I'll ask it to classify that just as I did before, and then I'll ask it to classify this 1.6 input and say, do we think that's male or female? And looking at the data, that seems kind of obvious. The only example we have of that is female, and yet the predictor says male. So what's going on here? Well, the problem here is that the classifier has no idea of context. All it sees is data. And one of the things it infers from this data is the majority of data is male. So if I ask it a question, already even before it's looked at the numbers, it knows that the answer is more likely to be male than female. Now, there might be contexts where that makes complete sense, that if this was predict the height of somebody in the male changing rooms, then that would be perfectly reasonable to predict that they're probably male even before you look at their height. But if this is supposed to represent a population, then we as humans know the population is split much more 50-50, and that the data here has been poorly collected, that there's a sampling bias, that for some reason the interviewer has gone out and asked more men than they've asked women. And if we look at the probabilities across the different heights, you see that while it makes a stepwise jump where all people below 1.75 m or so, it's decided are more likely to be female than male, actually the probabilities only jump from 35% to 22%, still minority probability of female regardless. And for that particular example, you'll see that that's backed up by the output prediction that it makes. So one tweak that we can make is something called class priors, and that's us injecting additional information into the system as humans, or there may be alternative ways that this gets computed that isn't in the data. And in this case, the class priors would say that before you start thinking about the values, here's our background probabilities that before you look at the data, it's 50-50 male and female. Now, in fact, you can inject this after the classification, although probably it's generally better practice in your code to put it in at the beginning so you can see as you read back your code that what you were doing. But by giving that adjusted piece of information, now when we look at this attempt to classify the 1.6 height, the probabilities have shifted, and it's saying, okay, given the background and the data, together we make a 57% prediction that the outcome will be female. And if I ask it just for the projection, it will simply take the most likely probability and say female. A similar but slightly different issue is unbalanced outcomes. And perhaps a good context for that is something like a medical test. So if the outcome of the test is that you get some cheap drug if you have the disease that will immediately fix you, and the outcome of having the disease is certain death, then any reasonable doctor who had the slightest hint that you might have the disease would give you the drug, unless there was some horrible side effect to it. So we aren't necessarily asking for the best prediction, we're asking for the best decision. And because the outcomes are so unbalanced, that the risk, the danger of, or the outcome rather, of predicting that you were healthy when in fact you had the disease is so disastrous, compared to making the mistake the other way around of saying you have the disease when you didn't, which has no negative consequences, we need to adjust the decision making in order to take that into account. So here's my toy example. I've got some inputs, some diagnostic measurement that gives numbers from 1 to 5, and anything from 4 above seems to suggest diseased. We'll put a classification on that, and we'll ask it what to do, what prediction it's going to make for 2.5. Now, we can now ignore the fact that that's necessarily the best prediction, because the probabilities say diseased is healthy is 58%, so therefore its best prediction is to say healthy. we're going to adjust that with what's called a utility function. And that's like attaching a score to each possible permutation of correct and incorrect predictions. So we've got two classes, so we have 4 permutations we need to consider. And so it goes up as a square of the number of classes. If they're healthy, then we're going to give the system 1 point for getting it right and no points for getting it wrong. But if the person is actually diseased, we're going to take away a point. We're going to punish the system for making a healthy prediction, and we'll give it a point for getting it right. So now, if it's trying to score the most points, it needs to err on the side of saying diseased. And now if we rerun that on the 2.5, the probabilities haven't changed, but the class decision has, because of this cost function associated with the punishing it or rewarding it for getting the right or wrong answers.